There are 2026 integers greater than 1 written on the blackboard, not necessarily different. In a move, computers chooses two integers m and n, both greater than 1, from different places on the blackboard and replace the two numbers with another two. The first one, the great common divisor of m and n, and the other one is a division, the least common multiple of the two numbers divided by the great common divisor of the numbers. This division is also an integer. He continues to make moves where it is possible to do so. Part A. Prove that regardless of the choices of computers, after finitely many moves, exactly one integer m on the blackboard is greater than 1. Part B. Prove that the value of m doesn't depend on the choices of computers. Proof of Part A. Assume integers m and n will be replaced by a and b. A times b is simply LCM of m and n, and the GCD parts are cancelled. LCM is less than or equal to m times n. The least common multiple is always less than or equal to any common multiple, and the equality holds if and only if m and n are relatively prime. In the case of relatively prime, the two replacing numbers are 1 and mn. We know 1 is the termination of a number in the process. A short summary. During the process of replacement, one of the two things has to happen. Either the product of the two new numbers is strictly less than the old one, or one of the new numbers equals 1, which no longer participates in any additional replacement. However, the product of all 2026 numbers is finite. So the strictly decreasing of the product can happen only finitely many times. If not decreasing, a termination number 1 will be produced. After finitely many steps, numbers are entering their final stage one by one, except the last number. Part B is slightly trickier, but also more interesting. It is always a good idea to start from a simple case when investigating a complex situation. Assume there are only two numbers on the blackboard, 2 to the 33rd and 2 to the power 12. In this case, their greatest common divisor is the smaller one, 2 to the 12, and the least common multiple is the larger one, 2 to 33. So, these two numbers are replaced by the smaller one, 2 to the 12, and a division, the larger one divided by the smaller one. We have 2 to the power 21. Continuing the process, we have a 2 to 12 and the division of 2 to 21 and 2 to 12, that is 2 to the power 9. Now, the largest common divisor becomes 2 to the power 9, and the division is 2 cubed. Repeating the process, we will go all the way down to 1 and 2 cubed. Let's go back and track how these exponents were derived. In the beginning, we have 33 and 12. Then 33 minus 12, we have 21. 21 minus another 12, that is 9. At this moment, 9 is actually the remainder when 33 divided by 21. The remainder when 12 divided by 9 is 3. Now you may see this is exactly the Euclidean algorithm for calculating the greatest common divisors. What would happen if there are more numbers on the board and more prime factors? Consider 3 numbers. 2 squared times 3 4, 3 to the power 8 times 5 cubed, and 3 6 times 5 6 times 7. For more than 2 numbers, there are choices which 2 numbers are to be replaced. For example, we can first replace the second and the third number. Calculating their GCD 3, 6 times 5 cubed and LCM 3, 8 times 5, 6 times 7. The second number is replaced by the GCD and the last number is LCM divided by GCD. It seems to be more complicated than the previous example, but if you look at the exponents of each individual prime number, say 3 or 5, they are still following the Euclidean algorithm. For example, let's check the exponents for 3. In the second and the third number of the original list, the exponent for 3 is 8 and 6. After the replacement, the exponents become 6 and 2. 2 is just equal to 8 minus 6. Repeating the process, you might choose a different path, but my calculations end up with 3 numbers, 1, 1, 2 squared times 3 squared times 5 cubed times 7. Let's check the last number. We have a 2 squared in it. In the original list of the 3 numbers, only the first number contains 2, that is 2 squared. All 3 numbers contain 3 as a factor. 3 to the power 4, to the power 8, and to the power 6. The greatest common divisor of 4, 8, and 6 is 2. And in the final number, we have a 3 squared in it. For 5, the second and the last numbers contain factors 5. They are 5 cubed and 5, 6. And in our final number, 5 cubed is contained as a factor. I'm not going to write up a detailed proof, but do want to list the key points. First, if 2 numbers being replaced contain a same prime factor, the exponents are L and S. Then, after the replacement, the greatest common divisor of the exponents remain unchanged, unless L equals S. In this case, the prime factor is gone from one of the new numbers. Secondly, we need to explain why order for choices of numbers doesn't matter. The theoretical basis is the associative property of the GCD operation. For 3 or more numbers, you can get the same GCD of all the numbers step by step, regardless of the order of the calculation. By part A, only one large number remains on the blackboard. The prime factors in the number are those ones appeared in the original numbers on the blackboard. The exponent for each individual prime number in the final number is uniquely determined by the largest common divisor of the positive exponent of the same prime number in the original numbers on the blackboard. I wish I'm not confusing you. Thank you for watching.